So have you ever wondered how you can create some cool VFX and magic effects in your games? You know, things like flames, wizardly projectiles, special auras, and all this super neat visual stuff that really brings a mage's power home. Well, today we're going to see that in our modern game engines, that's actually quite easy to do. Hello everyone, I'm Mina, and in this Godot 4 shader tutorial, we're going to discover how we can create a procedural 2D cartoon flame shader in GLSL code from scratch. As a quick reminder, the core idea behind shaders is to write code or to design graphs to define how an object should be rendered. Typically, its color, its glossiness, its surface distortions, and so on. A shader also tells the engine how this object should interact with the rest of the scene, be it the lights, the other objects that occlude it, or cast shadows on it, or even just the ambient lighting and environment. In a game engine, a shader is therefore a sort of render template with adjustable properties that you can instantiate as a material which has specific values for those properties. Oh, and just before we dive in, don't forget that if you want to support the channel and get some exclusive rewards like mini-games, tools, plugins and assets, you can check out my brand new Patreon. Plus, if you go for the highest Square member status, you'll even get to vote for future tutorial topics at least once a month. So feel free to have a look. Alright, now just before diving into the shader logic per se, let's quickly set up our scene so that we can test and demo our result throughout this tutorial. Since here we'll be working on a 2D shader, we'll need to use a 2D node to display it. This node can technically be a sprite 2D, a texture rect node, or even a color rect node, given all of those node types derive from the canvas item base type, but here I'm going to go for a sprite 2D. Then, to truly see something, we have to give this node a basic reference texture. This is required for a Godot sprite 2D to have a non-null size and to really get rendered in the scene. Now let's create our procedural flame shader as a new resource in our project, and in the creation pop-up, be sure that it's using the canvas item mode, which is what we need for a 2D shader. Okay, now in the material slot of our sprite 2D node, we're going to make a new shader material resource that uses this new shader resource. So what this means is that now whatever we put in this shader will define how our sprite is rendered in the editor and in the game. And if we click on this shader reference, you see that it gets auto-opened by Godot at the bottom of the screen, and we get our shader editor where we can write the GLSL code to define the shader logic. For now, the shader contains some boilerplate for a 2D shader. At the top we get its type, canvas item, which again means it's for 2D elements and not 3D models, and then below we have the vertex function that we could use for displacement, but that we won't use here, so let's simply remove it. Same thing goes for the light function at the end, that is commented out, and that could allow us to define a custom lighting for this object. But today we'll stick with the default lighting, so we can remove this method. Basically, the only function we're left with is the fragment function, that will define the color of each pixel in the render of our 2D element. To check that it works as expected, we can use it to render the UV coordinates of our sprites 2D. As a quick reminder, the UV coordinates are 2D points that define how a flat texture should be wrapped around an object's surface. In the case of a simple 2D quad, like here, they're basically normalized coordinates that go from 0, 0 in the top left corner to 1, 1 in the bottom right corner. Of course, for a 3D model, this can quickly get way more complicated, but here let's just keep it at that and assume that we have some nicely normalized coordinates in a readily available 2D UV vector. Okay, now at the base of our flame shader are going to be some procedural math noise textures. If you're not too familiar with that concept, I've actually already talked about it in this previous episode of the series, and in short, the idea is to use some specific math function that can transform 1D, 2D or 3D coordinates into continuous, pseudo-random patterns. In our case, those procedural noises will be a great way to mimic the random-like shapes in fire, so all the little turbulences and vortices that you see everywhere when you look at a flame. And this way we'll get something that is a bit equivalent, although of course we won't go for something realistic, and it will be way more cartoony. And guess what? The great thing is that in Godot we can create this kind of procedural noises directly in the engine in just a few clicks. So first, let's go back to our shader code and at the very top, export a new variable to define our procedural noise texture in. In a shader, those exported variables are what we call uniforms. So a shader uniform is a sort of public property that can be modified by the user, either directly in the inspector when you're in your game engine, or from your game code if you want to change it at runtime, for example. And these are the properties that we talked about earlier that can be different from one material instance to another. But anyway, in the case of a texture, the uniform should be of type sampler 2D, because in short it's a 2D thing that can be sampled point by point. Okay, so now in the inspector of our node, we can actually click on this variable slot and either load in a texture if we have some already prepared, or use the option at the very bottom to create our new noise texture 2D inside dynamically. And then inside this resource we can create yet another sub-resource that is our actual fast noise light instance. Then to visualize what we're doing a bit better, let's see how to actually get the info from this dynamic texture into our shader and apply it on our demo square sprite. So to read the data from a texture, what we call sampling a texture, in a GLSL shader, we need to use the texture built-in function. This function expects two parameters, first the texture to sample, and second the normalized 2D point to sample it at. Meaning here our UV coordinates, because remember that this code is executed for every point of our 2D object, so every point will use its own 2D UV texture coordinate as the sampling point, and we'll get back the right color for this specific position on the screen. Since this image is black and white, it has the same values for all of its 3 channels, so for example we can extract just a red channel of this basic texture and get back a float result that is the expected black and white patterns. Finally, to actually show the result, we need to write our color value to the output of our shader's fragment function, which in Godot, for a 2D canvas item shader, is the color variable. Now this is a vec4, meaning a vector with 4 coordinates, because it can hold up to 4 different values: the red channel value, the green channel value, the blue channel value, and the alpha or the transparency channel value. For now, since we only have a single float value, we're going to cast it to a vector3, so a vec3 variable, and assign it to the RGB channels of the color output. And we'll leave the alpha to its default value of 1, meaning it's opaque everywhere. And there we are! We now get a pseudo-random procedural noise built on our square sprite. Now, truth be told, you might need to tweak these noise settings for a while to find something that you like best. If you're curious about my own settings, feel free to check out this screenshot or look at the demo scene in my GitHub. Overall, I've slightly reduced the size of the texture, because I don't need that much details, and I've used an average scale Perlin noise with some extra warping. Okay, so suppose that you've somewhat configured your noise. For now, having just this big scale texture isn't enough. It would be really nicer to mix this with something a bit more detailed to simulate the complexity of real fire. We can do that by defining another similar uniform, so another sampler 2D variable, with another fast noise light that is smaller and slightly more detailed. Again, feel free to tweak it to your liking. Okay, so at this point we have 2 procedural noises. We have this one with a pretty large scale, and this one that is smaller. So now what we need to do is mix those 2 noises together. We can do that in various ways. This is what we call picking a blending mode or a blend operation, and it's key to making cool shaders. Now, there are a number of possible blend operations. Just to give you an idea, here's a page from the amazing Godot Shaders website with a list of snippets for various blend operations. In our case, a mode that can help retain quite a lot of luminosity is the soft light operation. So let's copy the code from the website, adapt it so that it uses floats instead of vec4 variables, and finally apply it to our two textures. And here we go. You see that this instantly gives way more detail to our flames, and it makes for a more interesting pattern overall. Just for comparison, here's a simple addition operation, where you see that it kind of gets just whitish everywhere, and here's a multiplication operation, where it turns into a lot of dark greys and blacks. So again, mixing your results the right way can have a big impact on your shaders, and I think that it's definitely one of those parameters that you should try to play with when working on a new effect. Okay, now one cool additional step could be to have the pattern fade to black at the top, since we want our final flame to start at the bottom and fade out to the top anyway. To do that, we can use the vertical y coordinate of our UV vector, since remember it goes from 0 at the top to 1 at the bottom. So it's basically a readily available black to white gradient that is normalized and that we can apply to our current flames pattern with a simple multiplication operation. If you want to better control where it happens and how fuzzy it is, you can use the smooth step built-in method, which takes in two parameters that define how close the black and white values should be together, so how high the contrast should be. It's a way to remap your low and high values. But in any case, we have something that's pretty good. We have a basic black and white effect that is reminiscent of fire. Although, yeah, I do admit, we're not quite there yet. Okay, now before we go any further, we need to discuss animation in shaders. Fire is one of these effects that can't really be static. It's all about the little cracks and embers popping everywhere, and the long flames dancing in the air. So, as is, there's no way our still noises can ever resemble real fire. But luckily, animating a shader is actually pretty easy. In Godot, you simply need to use the built-in time variable to access the current global time in seconds. It's available in any shader, and it allows you to apply movement to your effects. Typically, in our case, by adding this time value multiplied by an arbitrary factor to our noise sampling UVs, we can basically have those procedural patterns be translated over time. Even though, right now, you see it doesn't really get us anything good. And that's because, for now, our textures aren't made to be endlessly offsetted like this. To solve this issue, we need to do two things. One, at the top of our shader code, we need to tell those uniform textures to repeat, with this :repeat enable bit. This extra part is called a uniform hint, and in short, it's a way to give Godot some extra info on what this exported variable should be, how it's going to be used, and/or how it should be configured. In this case, we're telling it to repeat the texture so that if we sample it outside of the typical 0-1 UV range, we still get a result. The second problem is that now, as you can see, there are those ugly lines that show on our material at regular intervals. That's because, by default, Godot's fast noise light generator creates noises that are not seamless, or in other words, that don't properly wrap when copied multiple times. The solution here is super simple. We just need to go to our fast noise light resources and toggle on the seamless option to have Godot autocorrect this for us. And there we go. Our procedural noises now move vertically over time, and we're starting to get a somewhat interesting fire effect. But, of course, at this point, we should probably talk a bit about colors. Okay, now, so far, we've only been working with black and white float values. So we've converted our float to a vec3 with this direct casting, but all this does is repeat the exact same value on the red, green and blue channels, which means we're gonna get tints of grey. This is a nice way to prepare a shape and sort of draft your overall effect, but it's often not enough, especially in the case of flames and fire. To turn our grayscale mask into a colored equivalent, the trick is to do the following. First of all, we're going to define some new uniforms at the top of our shader, a light and a dark color. You see that as in any GLSL shader, we're using vectors with 3 coordinates for the red, green and blue channels, and that we can then give them the source color hint to have the engine show these variables with color pickers in the inspector. Then in our fragment function, we're going to use the mix GLSL built-in to have our black to white flames be remapped to these colors. Basically, whenever the mask was black, we'll get our dark color. Wherever it was white, we'll get our light color, and for all the grey tints in between, we'll get a mix of the two. So to see this new vec3 mixed color variable, we simply need to assign it to the color.rgb output of our shader instead of the previous flame shape. To further enhance the burning effect, we can also add some white at the very bottom of the shader, because this will make it look like the whole thing is even hotter, with the source points, the emission points of the flames, being white hot. To do this, we can redo a second mix operation, this time between our current blended color and a pure white vec3. For the interpolation value, we can use our vertical coordinate of our UV, so that the white is applied only at the bottom. And if you want to better control the position or the fuzziness of the transition, you can once again reuse the smooth step function. Finally, to really give it this look of crackling fire filled with energy, it would probably be better to boost the overall tint, cause for now it looks a bit dull and powerless. So what we're going to do is export a new float uniform in our shader called emission, that defaults at 1, but can be used as a basic color boost. If we multiply our mixed color by it, and then increase it in the inspector of our node, you see that we get brighter, more vibrant colors. So here we are. At this point, we've successfully transformed our black and white mask into a blend of colors that really give our shader more of a fire effect. Meaning that if you want to do some plain fire effect, a flat surface or a curtain of fire, for example, and you're looking for this cartoony 2D look, then you might want to stop there. But if you want to go for something like a magic fireball or just a flame over a torch, then you might want to go one step further and see how to give this UI element a real teardrop-like flame shape. Alright, now in order to apply this teardrop mask, we're going to take advantage of the fact that the Godot node we applied our custom material on is a sprite 2D. Cause even though for now we've used a simple white rect texture to visualize our results, we can of course use way more advanced images instead, and those images can do more than just forcing a non-null size and giving us reference UV coordinates. Indeed, suppose that we have this black and white mask image with our teardrop shape white in the middle. Basically, what we want to do is have all the black parts become transparent in our shader and all the white parts stay opaque. Okay, so if we put this texture in the texture slot of our sprite 2D node, we can actually sample it directly in our shader code as the built-in texture variable, which gives us a reference to the texture used by the node this material is applied on. So since this image is black and white, it has the same values for all of its 3 channels. So for example, we can extract just the red channel of this basic texture and get back a float result that is the expected black and white teardrop. And of course, we can then super easily use it as a transparency mask by putting back our colors from before in the RGB channels and instead assigning this grayscale float to the alpha channel of the shader's color output. That being said, right now our flame does still look a bit weird, because it's sort of too dense everywhere. What we like is for the upper part to appear more and more transparent as the flames fade into smoke. To do this, we can reuse the same vertical coordinate trick as before and use it to create a vertical black to white opacity mask. So basically, by multiplying our previous mask by this vertical grayscale gradient, we'll easily get our density progress from bottom to top. And actually, to improve this transition a bit more, we can also reuse our flames black and white procedural noises from before. If we apply them on our mask with another soft light mix operation, then you see we can improve the top fade out a bit and get something slightly more realistic. Though yes, it's still a clear-cut 2D cartoony shape overall. Okay, so at this point we have a really cool flame effect that's starting to look very neat. But there is still one extra thing that we can do to boost it a touch more. Okay, last but not least, let's see how to add some distortion to our flame. This might not seem like much at first, but if I show you a before-after, you see that this really adds a lot to the effect, and it helps sell the aliveness of our fire. So to have our teardrop shape wobble over time, we're going to do something similar to our noise animation. We're going to use the built-in time variable to sample our drop mask texture in different locations over time and thus simulate movement. More precisely, let's start by duplicating our UVs as a new vec2 variable and use this new copy in our mask texture sampling. Then you see that if we change the x coordinate of a UV, we indeed get a horizontal shift, and so we can basically move our mask around. Now, the trick is to find an algorithm, a logic, a function that can actually create sort of waves. In fact, something important is that we want to get a periodic and continuous result, so that we get cycling repetitive deformation patterns that can shrink and grow indefinitely, and we don't get a sudden cut between the horizontal positions of our wobbly pixels, but instead we have a nice curvy deformation. Now, if you're a bit familiar with shaders or with maths, you probably already know where we're going with this. I talked about waves, I talked about periodicity and continuity. Basically, we're going to use a trigonometric function. So, for example, if we increase our x coordinate by a cosine s, to which we pass the vertical UV point position and some arbitrary time-based offset, then you see we indeed get something. Now, the problem is that, for now, this cosine s has too big a frequency, so it makes for a pretty ugly result. But if we multiply the vertical coordinate by a small factor, then you see it's starting to get a bit easier on the eye. And then, if we reduce the overall amplitude of the displacement by multiplying the entire cosine s result by a small factor, we get something way wobblier. Now, at this point, it might also be a good idea to have this displacement impact the top of the flame more than the bottom. So once again, we can reuse the vertical coordinates of our pixel to change the strength of the distortion, and make it more impactful at the top than at the bottom. Of course, if you want, you can also extract those two parameters and turn them into user-controllable uniforms in your material to make it easier to set the strength and the speed of this displacement, or even remove them altogether. But in any case, here you go! You now know how to create a procedural 2D cartoon flame shader in Godot 4 using GLSL code, some basic textures, a few procedural noises, and a bunch of mathematics. Now, I really hope you liked this video. It was a bit longer than usual, but I felt like it would be better to talk about a variety of shader tricks. Don't hesitate to tell me in the comments if you liked this format, if you want me to talk more about shaders, and of course, I want to thank all of my Patreons for the support and their ideas. In particular, a huge thank you to my Square member, René Hitzke. Also, if you enjoyed this video, feel free to like it, subscribe to the channel to not miss the next ones, and perhaps even drop a comment with ideas of Godot tricks that you'd like to learn. As always, thanks a lot for watching, and take care!